All right, so in the lab that we're going to be doing this week, then what we're going to be using is polar graph paper to map the orbit of a binary star. So let me explain polar graph paper for those that haven't used it before. It's this circular sort of graph paper right here. And the way that it works is that you want to measure the angle around this way and the distance out this way. So for example, for one of the stars, you would say that the center is 0, 1, 2, 3, 4, 5. So you might say that you have a binary star and its initial position is at 45 degrees and 4.5 arc seconds. So you'd go out 1, 2, you'd find 45 degrees. It'd be 1, 2, 3, 4.5, and you put a dot right there. Okay, and then the next one might be at an angle of 80 degrees and at 4.1 arc seconds. So you find 80 degrees, you got 1, 2, 3, 4.1, and put a dot. And then the next one would be maybe at 120 degrees and at 3.9 arc seconds. So you find 120 degrees, go out to 3.9. And the next one might be, for example, at 149 degrees at 3.9. So the same thing. And then you might have one that is going to be 182 degrees, and it might be at 3.5. So you go 182 out to 3.5. And then the next one might be, these aren't going to be actual numbers you have, but the next one might be, for example, at 235 degrees and at 3. So 235 and then at 3. And the next one might be at 265 and at 2.8. And you find 265 and 2.8. And then the next one might be at, let's say, 290 degrees and 3.2. And so 290 degrees, 3.2. And the next one might be at 333 degrees and at 3.3. Okay. And then the next one might be at 5 degrees and 4.0. And so 5 degrees, 4.0. And then when you're done, after doing that, it has traced out an oval shape like that. All right. And so that oval is going to be the orbit of your eclipsing binary. And so what you would do is you would find the farthest point here. That would be like the apices, the nearest point to the periapsis. Okay. You could do that. You could figure out how long it takes to go around. That gives you the period. But you also want to know the semi-major axis. So that is going to be half of the distance across. So you find the longest distance across, and you find the longest distance across, and you measure the longest distance across. Then what you want to do is you want to find out how long is that. So what I would do is I'd find the longest distance across, and then I'd lay this down right there. 1, 2, 3, 4, 5, almost 6. Okay, so I don't just measure out. What I do is I measure this, and then it doesn't even have to be a ruler. Okay, it doesn't even have to be a ruler. It can just be a piece of paper, and I measure that distance right there, and I lay it down here, and the center going out, because this is your scale right there. I lay it in the center going out. It doesn't really matter which way, and I count how far out that is. That's the major axis. That's the distance all the way across. What we want is half of that distance. So whatever you measure that to be, divide by 2. And so that will be what you need in order to figure out the semi-major axis of that orbit. Okay, and then we know that total mass times p squared equals a cubed. So that means that the total mass is going to be a cubed over p squared, where a is that distance right there in AU. P is the period in years. Now, to get the distance in AU, what you have to do to get the AU is you multiply the distance in parsecs, and you multiply that by the separation in arc seconds. Okay, this is arc seconds right here. So what you found was, when you made the measurement, you measured it in arc seconds, and so you found the A in arc seconds. You don't want it in arc seconds. It has to be AU for the equation. So you take that distance that you measured there and multiply by the distance of that star in parsecs. You found the distance in parsecs on the previous page, because it gave you the parallax of the star. You know that the distance is 1 divided by parallax. And so this lab kind of takes several of the things that we've been doing and puts them all together in one spot.